Good morning and welcome to today's notes on pretty much just applications of differential equations where we're given the differential equation, we're going to solve the differential equation, and then we're going to use the solution to the differential equation to solve a few problems that we have. So we're going to go back to a lot of the formulas that we used back in our differential equations back in the first section 1.3, where we were talking about Newton's law of cooling, population growth. And so we're just going to use those, and we're going to be able to solve those differential equations to help us determine, okay, what does this model look like. And so for the first one in this section, we're just going to solve some linear first order models that were introduced in section 1.3. So example 1, we're going to talk about population growth. Population of a town grows at a rate proportional to the population present at time t. The initial population of 500 increases by 15% in 10 years. What will be the population in 30 years? How fast is the population growing at t equals 30? All right, so let's go ahead and solve. So it tells us that the population of town grows at a rate proportional to the population present at time t. So that's how we're setting up our differential equation. So that's why we have dp over dt equals kp. Now we want to go ahead and solve this differential equation because we're given some information about the initial population and how it's growing. So dp over dt is equal to kp. It's a separable equation. So we're going to get all of our p's to one side and t's to the other. So we'll have dp over dt over p is equal to k times dt. Then we're going to integrate both sides. And so the left-hand side, we're just going to have natural log of p. And on the right-hand side, we're going to have kt plus c. Now again, we want to solve for p, so we're going to take the exponential to both sides. And so we're going to have p is equal to e to the kt plus c. It's going to be c times e to the kt. And now, since we're talking about initial population, that c is going to be the initial population. So we're just going to change this to p is equal to p sub 0 e to the kt. All right, now let's look at some stuff. The initial population, let me box this up so that we know, okay, this is our solution to our differential equation. So the initial population of 500 increases by 15% in 10 years. So we know that our population after 10 years has increased by 15%. So we'll be able to solve for a few things, namely our k. So let's go ahead and set that situation up. So again, I'm setting up this situation. The initial population of 500 increases by 15% in 10 years. So go ahead and say, so what's 15% of 500? It's 75. So now we're at 500, our population is at 575, and that's equal to our initial population, which is 500 e to the 10, that's how many years have passed, k. And through this, we're going to be able to solve for 500. So let's go ahead and solve. We're going to divide both sides by 500, and so we're going to get 575 over 500 is equal to e to the 10k. Let's get rid of the e by taking natural log to both sides, so we're going to have natural log of 575 over 500 is equal to the natural log of e to the 10k. Natural log e is going to cancel out, so we're left with 10k, and so now k is equal to 1 over 10 natural log 575 over 500, which is 1.15. And then doing the math there, we'll go ahead and leave it this way until we apply it, because we're going to have to be rounding. So we'll just say 1/10 natural log 1.15. Now, we solve for our k using our information from 10 years is 15% increase of population. What will the population be in 30 years? So let's go ahead and find what the population will be in 30 years. So we want to do P of 30 is equal to P sub 0, which is 500, e to the 1/10 natural, that's an ugly natural log of 1.15 times, so that's our K value, and then our T value is 30. And then all we need to do is just plug this into a calculator. That 1/10 and 30 we could multiply just to get 3, but we'll just plug this all into a calculator, and it's going to be about 760 years. I'm sorry. The population in 30 years is going to be 760. All right. Now, we answered this question right here. What will the population be in 30 years? And so that's going to be 760. And then we are going to find the solution to the last part, which is going to be how fast is the population growing at t equals 30? So how fast is it growing at t equals 30? That's we're going to plug that into our derivative. So p prime of 30 is just equal to k times p of 30, going back to our initial differential equation. All right, and so that's going to be our k value, which is 1/10 natural log of 1.15 times 760, because that's how much our population is at that time, and we get 10.62 persons per year.